All right, and then in this particular video example, we are going to apply our work in finding definite integral into finding the work where we're pumping water out of a container. Okay, so the idea is hard to describe verbally, but let me quickly draw a picture right here, and then we will have a better idea of that. So let's just assume that we have just a standard tank right here. Okay, and water, as you already, anyone watching this video, as you have already aware, water is heavy. Okay, water is heavy, and so now think about, we have a tank full of water. We have a tank full of water, and then so now here's water, and I said full of water, but let's just for now say right now we're at the instance where we have a certain depth, y right here. Okay, and the tank here, it has a certain depth, and then it has a width right here. Okay, it has width, and the tank here got length. Okay, and rectangular shape of the tank is just standard, but then be ready for other shapes of the tank as well. Okay, so I have we can also apply that to the kind of tank where the cross section here, the face here is like that, and then it's rectangular on this, and people call this it's a trough. Okay, it's a trough. Okay, it's a trough like that. Or it's a swimming pool. It's also a tank, nice circular shape, and the idea is how much water is in there. We try to pump it out. So pumping water out of that, here's the plan. So out of so many different shapes of the tank right here, allow me to focus on one shape right for now, because the shape is not the important thing. The plan of how we pump the water out is the thing. Okay, and so water itself, there's no way to grab, and especially we cannot lift the whole tank and dump it away. Okay, imagine that we have a very big tank, like a tank for where, like at a water reservoir or something like that. Okay, so we can't just take the tank and dump it out. Okay, so no luck doing that. And of course, think about the tank here. It has a certain height, so taking the water out means we have to lift the water up, and that's what I'm trying to explain right there. So we can't just lift the tank up and dump it out. So it does take some work doing that, but the plan seems simple that way, but it's almost impossible to get it done. So don't even think about it. Lifting the tank up and then pour it away. It takes a lot of effort. So that's why we have to pump it out. And so the idea of pumping it out now is that we're going to withdraw the water out by thin surfaces of water. We're withdrawing, so we're taking thin slices of water and take it out. It goes by. So as we keep taking it out, then the depth of the water keep losing. Okay, and so at any instance, so the idea now is at any instance of water depth here, we're taking just simply one flat slice of water surface, very thin slice of the water surface, taking that and lift it out. Then the water surface, even though very thin, but it has a thickness, it has a volume, right? And then of course water has its own known density. And then as we lift it out right here, either we're using machine to pull it out, but it goes one by one. So slices and slices of water being lifted out, being pulled out, like that, being pumped out of that. Either we're using the whatever that is, but machines or our own hand tool right there, then it's still going to take. The idea now is that instead of taking the whole volume of water to dump it out, we're going bit by bit. Okay, we're going bit by bit. Okay, and so this is highly recommended. Again, just like any other, at this point when you arrive at this example right here, I'm pretty sure you have seen my other examples. So in any example I introduce, you have to watch the examples in connection. And after you have watched my general lecture where I talked about this kind of problem where we apply definite integral into doing work. And so in my general lecture introducing the problem about applying the definite integral into finding work, it's a physics problem. Then I brought in the concept that think about a man that's pushing a heavy crate right here, okay, a heavy object. Instead of cranking all of his efforts to push that object along the path right here. He also can do the following. He can imagine that the object, that crate contains, that container has a whole bunch of little pieces of mass in there. So he can just lift one out, pull it out, lift another one out, okay, pull it out, and lift another one out, and pull it out. So we carrying things bit by bit. And so each one of those has a little mass, but as he brings that in a distance right here, he has little work for each one to lift all of those, and eventually he's going to finish out the whole crate instead of pushing the whole crate along the way. Okay, so the plan is like that in this problem right here. Instead of trying to dump the whole water and lift the whole water out, it's dangerous for us, right? It's impossible for our physical over here. So we're going to lift bit by bit a thin slice of water, which will have a known volume and eventually a known mass, where we need a known amount of force, a calculatable amount of force to lift it out. But it's known, and then we lift it. How far do we lift? We lift that. See, suppose we're at any certain depth of the water, then we, from the total height of from the total depth of the tank, then we're gonna have that much distance. So this is the distance to be lifted for each slice of water. For each slice of water, this amount right here is the amount of distance to be lifted there. So that's the distance to be lifted. Okay, so we have distance to lift each one of our thin slice of water. And right now I'm using just a rectangular box shape of a tank, but be ready for any shape. But the idea is all here. We're taking thin slice of water, so from the top down first. So always the top one goes out first, and then once it already got out and we have whatever left, the top one there of the remaining one gets pumped out again, and the top surface again of the top thin slice gets pumped out again. And we keep doing that until the amount of water, the water level decreases and decreases until we got none left. Okay, and that's the idea, and that's the plan for this problem. All right, so needless to say, so as I have already mentioned, so this lecture here is highly recommended to be watched after you have seen my general lecture about how we apply definite integral into doing work as a famous or standard physics problem like that. Okay, and so now I am going to swing over to the wording description on my computer screen right here. It does get a little lengthy, but I'll try to break it down and extract out the most attention-grabbing information fast. Okay. All right. So let's now look at the worded description of our problem here. So a trough is 6 feet long and 1 foot high here. Okay. So 6 feet long and 1 foot high. So I had the picture of the trough earlier on the board. So let's now get a formal drawing of that trough right here. So my trough has a shape like that. Okay, some kind of bent shape here, and then it's open end up here, but well, 6 feet long. So this is the length right here. Okay, and let me try to put it, I'm trying my best to put it in perspective a little bit. 6 feet long, okay. So there's my trough. All right. And so this is the cross section right here. So 6 feet long, this length right here. All right. That's 6 feet, and this is that trough like that. Okay, and so we're filling this trough with water, and don't worry about the stands or whatever, however we can stand it, but this is how it stands up, okay? And then it's our trough right here, our trough. So being 6 feet long, and it's full of water, and then 1 foot height. 1 foot height, that means the total height from here down to the bottom. Okay, that's 1 foot high right here. I might be upscale, forgive me on that, but maybe because I'm trying to put that in perspective right there. So 1 foot high. Okay. All right, so that's a good enough understanding of our trough right there. So now let's get back on the wording description and say, and let's look further. Now the vertical cross section of the trough parallel to an end, that's parallel to an end, is shaped, okay, shaped like the graph of y equals x squared from x equals -1 to 1. Okay, so very fancy description, but see, it talks about right now, it talks about the vertical cross section. vertical cross section. Okay, vertical cross section of the trough, right? Of the trough here, parallel to an end is shaped like the graph of that, the x squared y equals x squared function. So that means, see, that's why I'm attempting my best to draw the shape like that nice parabolic shape right here. So this end and that end, they are supposed to be parallel. Okay, and let's assume that our trough here is that simple case. This end and the other end, they are the exact same cross section shape like that. So now the problem brought to our attention that it's shaped like, that's why it's our choice right there to later on use an equation. But the shape here is like the shape of that parabolic the function from that parabola of y equals x squared. So, and then from x equals -1 to x equals 1. That's the description right here. And so now reading that description, here's how I see it. From that description, I can think about putting the x-axis. I mean, it's for now. It's a little early right now, but we can always think about putting the x-axis because it's the way how any parabola is. It's the way how any parabola is. That we can, the bottom of that parabola, the bottom of that bow shape right there. Okay, so this is 1 foot. Okay, but the bottom here has to be the vertex of that parabola. So we can imagine that there's the x-axis, I mean there's the y-axis pointing up that way. So we can call it the y-axis, which is the vertical axis. Okay? The y-axis is pointing up that way. And so 0 is down here, and then you can think about this is the x-axis. But this height right here from the bottom to that, so x equals 1 is here. That's the right end of the trough, of our trough right here. And then this is the left end of our trough. Okay, x equals -1. And that's how we have, so see in that parabolic shape of our y equals x squared function, then when it reaches that, then we have a height to y equals 1 right there. That's why we have that depth. Okay, so now that's the information that we want to see a little more into our problem right here. But now let's swing back to the wording description of our problem. So the trough here is full of water. And then we want to find the amount of work in foot-pounds. Okay, so now it brings a sign that our problem here is being measured and being calculated within the American convention right here. Okay, where we're using feet, and see it's 6 feet long, 1 foot high, right? And then the work here is the amount of energy here is measured in foot-pounds right here. So find the amount of work in foot-pounds that's required to empty the trough, right? By pumping the water over the top. See, pumping out the water. And we don't even have to say over the top. It has to be over the top, as long as we're pumping the water out of that trough right there, because the trough has only the open top. Okay, and then this is another important information right here. In this problem, let's use 62 pounds per cubic foot as the weight of the water. I will get to that information later. Okay, but now with that shape right here, once again, the water is completely full for this trough right here, okay, from the beginning. So when we begin, the water is all the way up there. But then now I want to draw the following picture that hopefully will trigger your imagination. That think about in my explanation earlier. Then the idea now is there's no way to take the whole body of water and pull it out. It's water, it's liquid. There's no definite shape. So how can we even grab it? Okay, to lift it out. So in that way, we think about we're using machines or whatever tool that is to pump out slices and slices of water, thin, infinitesimally thin slices of water from top out. So it keeps going top out, and top out until, so as we keep pumping out the top slices of water, the amount of water gets lessened, get lessened. Okay, and to the point that, so let's say at some point, at any instance where our water reaches a height, where our water reaches down to a depth of only y. You see, so that's why it's important here that we put the axes on. That helps us to help a reference. Okay, so there's our water level. So when we're at, so this is y right here. Okay, this is y. I'm going to call that y because as we keep taking out the amount of water, then we have y amount. Our y right here is the amount of water level left. Okay, so in that way now you can see that y will keep getting reduced and reduced and reduced. Okay, whereas we are pumping out water, pumping out slices of water. So in that way now I'm gonna define my variable. So I'm gonna let y to be the current. Okay, the current depth of water, and this is in respect to the vertical axis y right there. Okay, because it's about how deep the water is, and then we keep withdrawing the water right there. And so now when we're at that any current depth right here, then that means think about the thin slice of water right here that I'm trying to put my marker over. Think about that thin slice. If we're trying to take, and in my explanation, if we're withdrawing that thin slice of water out of the trough right here, then the distance to remove the, so 1 minus y, okay, is the distance. This is important right here. 1 minus y is the distance, okay, to lift or to pump. Pump is a different way of lifting the water out of that. Okay, so 1 minus y is the distance to lift the top thin, and when I'm saying thin, it's infinitesimally thin. Okay, to lift the top thin slice. Okay, out of the trough, the trough. Okay, out of the trough. That's what it is. So at any thin slice, we keep removing it out of that. So this distance right here, that's 1 minus y. I'm hoping that I can make it clear enough in a picture that has so much information already. 1 minus y. Okay, and then I'm indicating right here. So 1 minus y is the distance to lift the top thin slice, right? And of course, the top thin slice of water to be out of the trough. Okay, and so now, so we got distance, but how do we figure out how much force to lift? How much force to lift the thin slice out of in that distance? And that's the next thing, because remember, work is always about we exerting a force. We applying a force to move an object a certain distance. Okay, and here we know that we're moving a thin slice of water to that distance. We already had a general expression of the distance, but how do we know how much force required to lift that thin slice of water out of the trough? Okay, so here's how it works. You see, look at the picture right here. Then we have a way to actually figure out the volume right here. You see in the way how it looks right here, the length, okay, the length of the, I'm gonna start going brief here a little bit. So length, and of course it's length of the one water thin slice right here. So length is going to be this length, 6, because it's just the same fixed shape with that length of the trough. Okay, and now the width here, it's different depending on how deep we are. Depending on how deep the water is left. Okay, so now I'm going to say the width of the water. Had a little bit of a misspell right here, but no, the width of the water is actually, so this width here, and the good thing is so it depends on the cross section, the shape of the cross section, which was already, we knew that the cross section here came out as the shape of the parabolic equation, y equals x squared. Okay, y equals x squared. But y equals x squared, but now everything is on the x-axis right here. We're talking about at any depth y, because mainly it looks like so far I'm driving your attention into using y as the main variable, and y is going on this direction right here. So y equals x squared. That means square root of y equals x. That's how it happens. Or allow me to write this on a separate space right here, or on the other side. This means the same as square root of y equals x. Okay, so having y equals x squared lead to square root of y equals x. Technically, we can also go with this side of the parabola is negative square root of y, but just stay with it's symmetric, so just stay with the positive side right here. But now so that means this height right here is square root of y. Okay, because when you're down to that depth right here, that length right there over, that's x equals square root of y again. But that's not really all of that. The whole width is this, double of that amount right there, double of that amount. So really the width here is 2 times square root of y. That's how I'm seeing it. Okay, 2 times square root of y. So now we got length, we got width. Okay, what's the thickness? The thickness in here, again, everything is, right now we're standing the trough like this, vertically standing up, and that parabola is pointing up like that. So the width has to be just the width is, let me draw that in a different picture right here. So if we think about the slice of water like this, that's the slice of water, right? If we look straight into the cross surface of that, then the slice of water has thickness being a dy. Okay, the thickness of that is being a dy in the way how we place our trough. Okay, and so in that way right here, now I'm going to indicate further. So thickness, or the depth of one slice, the thickness of the slice right here, the slice of water that we're removing out. So thickness here is dy. Okay, so we got length, width, and thickness. We are ready to find volume of one thin slice to be pumped out, to be lifted out. Okay, to be lifted out of the trough right there. All right, and so now I'm ready to advance to my other board right there. And so in that way right here, I see that volume, okay, volume of each slice equals 2 times 2 squared root y multiply with 6, okay, because this is length, this is width, multiply with dy right here. That's volume of one thin slice. So volume of a slice, okay, and of course when I'm saying a slice right here, I mean a slice of water, okay, volume of a slice of water. And so now there's one more little step left. Once we've had volume, then we're going to, and this is of course measured in cubic feet, and so now I'm going to talk about weights. This is really the amount of force right here, how much force we need to lift this much water out of the trough. Okay, this is the amount of force. So first of all, let's swing back one more time at the wording description. Okay, so we're pumping that over the top, but in this problem, see, now it's time to make use of this useful information. Use 62 pounds per cubic foot as the weight of water. All right, so really what it means here is we have the density weights of water, 62 pounds per cubic foot. That is in American convention right there. All right, so that means now with this much volume of one thin slice of water, so it's not the same amount of volume. It's different as we get deeper, as the level of water keeps losing, right? As the current depth of water keeps losing, then each slice has that volume right there, generally determined by that formula. But now we're going to multiply 2 times square root of y, okay, times 6 times dy, and now we're going to multiply that with 62. All right, so that's the thickness, and that's the width, that's the length, okay, and that's the density. Think of that as a density, weight density, okay. And so now all together, so now at this point, this is force. So now I'm going to use the force and multiply with distance. So for any thin slice and at any current thin slice on the top like that when we're moving it out, when we're pumping it out of the trough or lifting it out of the trough, then we need this much force. Okay, so, and then let me multiply all this together. 2 times 6 is a 12. 12 times 62 times square root of y times dy. Okay, that's the amount of force, but then we need to multiply that with the distance 1 over y right here. We need to lift this much. We need to exert that much force to lift the top thin, infinitesimally thin slice of water out of the trough by going this far distance, 1 minus y. 1 minus y is the distance to lift the top thin slice out of the trough right there. Okay, and that's the idea right there. And so now all of that here, ladies and gentlemen, this is little amount of work right here. See, because force multiplied with distance. This is force. Okay, we call it weight in daily term, but that's force right there. And this is apply in a distance. All right, that's apply in a distance, and that's how I come up with my the little work amount. In the sense that we take that into 1 bit of work amount, lift that thin slice of volume out of the trough, and then we're going to do the next one and the next one and the next one, and we keep accumulating all the little work amount until we finish the whole trough. Okay, and that's the idea right there. And so now I need the board space, so I'll allow me to erase all of this here and put that all into a complete integral, because the idea now is that once we have a successful expression of all the little work amounts of any little work amount, then to get the total amount. And sadly I didn't leave this here for too long, but all right, so total work is famously known, and again this is extremely important that you watch this video lesson, this video example after you have seen my general discussion lecture about how we apply definite integral into finding work as a physics problem. Okay, so total work will be equal to accumulation. We're accumulating all of the little work amount from a start to an end. Okay, and that means we're accumulating all of those. So the expression now is going to be 12 times 62 times square root of y times 1 minus y. I'm rearranging the order of these factors expression a little bit. Okay, but so 12 here came out from 2 times 6, so 2 was 2 times square root of y times with 6 right there. So that those two are together the volume, and together with that the dy right there, that's the volume, and then multiply with that, it's the weight, and then we multiply with distance. But I purposely write the dy at the very last right here. Okay, and we have a start and we have an end. Okay, so let's check for consistency before we move on. Well, it's a little bit unusual in the way how I approach that. Usually I try to come up with the d expression first, but now in this problem I derive the variable first. I came up with the variable first, and then we check for a consistent that we found, hey, there's a d expression here, and our d expression is in terms of y, which is also consistent with the variable that we designed previously. If it's not, there will be way. If it's not, there will be way to change our variable, to re-express our variable, or change our d expression to be consistent with the main variable. Okay, and at this point that you are viewing this video lecture, then you have been exposed to enough technique in taking integral to get that task done, meaning, make your variable the variable indicated in the d expression here to be consistent with the main variable. Okay, so this is the accumulation, and now we just simply need to look for where we're starting our accumulation and where we're ending our accumulation. Okay. All right, and so back to the picture, and I can see all the accumulation, and as we're placing the picture vertically up like this, then we're accumulating those thin slices from the bottom up to top like that, right? Those slices. Okay, and so y equals 0 to y equals 1 right there. Okay, and that's going to be our accumulation. And so now we're going to have a start at 0 on the y-axis, and the end here is at 1. Okay, at the top of that picture right there. Okay, all right, and so now it's just a matter of getting the problem that we now have. At this point, we have a complete setup, integral setup right here, and that always I stay close with the fundamental that an integral is accumulation. Here we're accumulating the amount of work that needed, each little tiny bit amount of work to lift, slices and slices of water from the bottom up. Okay, so now we are going to apply the fundamental theorem of calculus to complete out that integral work. There's no need to multiply the 12 and the 62 right now. They are just coefficients, so I'm going to keep them in front. So it's going to be 12 times 62, and multiply with the integral from 0 to 1 of 1 minus y times square root of y dy. Okay, and then before using the fundamental theorem of calculus, I am going to work out the algebra a little bit on these terms right here. Okay, so that gives me, now notice that the square root of y is the same as a y to the 1/2 power. Okay, so I'm going to multiply that to each term and distribute that the y to the 1/2 power to each term right here. So my integral in the next steps becomes so 12 times 62. Okay, we're multiplying with the integral from 0 to 1. First term becomes y to the 1/2 power minus y to the 3/2 power algebraically. Okay, and that's with the dy. Okay, so that's y to the 1/2 power multiplied with y. That's how I ended up with y to the 3/2 power. 3/2 power. All right, so now, as I said earlier, I am going to use the fundamental theorem of calculus to get this done right here. All right, so to get it, but then in case anyone has not been familiar with what the fundamental theorem of calculus is, then you must exit out or pause this video and find my other video lesson where I talked about what the fundamental theorem of calculus is. And then once you know what the fundamental theorem of calculus is, then we can go back and resume this lesson right here. Okay, so needless to say, this is also recommended to be viewed after you already know what the fundamental theorem of calculus is. Okay, so now in that way, I'm going to keep the 12 times the 62 here as a coefficient. Fundamental theorem of calculus says I'm simply just going to take the antiderivative of that y to the 1/2 minus y to the 3/2, which gives me 2/3 y to the 3/2 power minus 2/5 y to the 5/2 power. And then this antiderivative will be evaluated from 0 to 1. Okay, and so now in that way, that's the same as I'm now simply just going to substitute each integral limit here into our antiderivative. So 12 times 62 as the coefficient. Okay, and I'm going to multiply with 2/3 times 1 to the 3/2 power minus 2/5 times 1 to the 5/2 power. Okay, and then the good thing about the zero limits here is that when we're substituting that into our integral here, it's going to be a 0 out. So I just simply save myself some effort by writing a 0 there. Okay, so now I'm going to quickly step over to my computer station to get the final calculated answer for this. All right, and so the final answer I've used here is going to be 198.4. But so watch out again. As we have seen back in the wording description, this problem here, everything is measured in the American convention, in the American standard for units. So here our final work units here has to be foot-pounds right here. So that's foot-pounds. Okay, 198 foot-pounds right here. All right, and that is how we're solving this problem. Okay, and so this is an example where I point out that the idea now is that just like back in the general discussion lecture, I talked about that if we're trying to do all the work all at once being too much, then we're going to take it out bit by bit, right? And then doing that, and then we're accumulating all the little work, and that's the kind of problem that exists here right there. Okay. All right, and now let's look at another problem, and we could call that part B of our application example here. Okay, even though it's two separate different problems, but it's the same class of problem where we're pumping water out of a tank. So let's read the wording description of the problem here. So what we have is a circular swimming pool. It's a huge tank of water, that's all. Okay, a circular swimming pool has diameter of 20 meters. So now in this problem, unlike part A, then we are switching back, and in this problem we're switching back by using the SI units for every measurement. Okay, so a circular swimming pool has a diameter of 20 meters. The sides are 4 meters height, right? And the depth of the water is 4 meters, so it's completely full of water. Okay, and so now how much work in joules, of course. So now we're back in SI units. How much work is required to pump all of the water over the sides? Okay, and it's slightly different with the wording here over the side, but really what it means is simply we're gonna just take slices of water and pump it out over the top so that it gets splashed out on the side of the pool. But so I actually, technically we don't need to see this example, but I brought it up as extra example, as an extra experience for viewers, whoever happen to watch this. So if you feel already good enough with your understanding about the idea of pumping water out of a tank from part A right there, then feel free to exit out of the video here, because the problem here is pretty much exactly the same, where we have a different shape of the tank, that's all. Okay? And then due to the different shape of the tank, it's going to help us. It's going to come up with different ways of deriving the integral, that's all. But in the end, every fundamental I carried out, every step I carried out from part A is again being done here in this particular example. Okay, so now one more time, let's continue looking at the wording right here. So we have acceleration due to gravity is 9.8 meters per second squared, and that will be later on useful for calculating the force that's needed to lift water out. And then we have density of water to be 1,000 kilograms per cubic meter right here. Okay, so now let's get back from the beginning. Let's extract the information in the beginning here. A circular swimming pool with a diameter 20 meters. Okay, and then the sides are 4 meters high, and of course it's full of water. So let's make a sketch. So even though we know that we start out with a tank full of water, but just allow me to draw. So how about this? All right, so there's our swimming pool. Okay, 4 meters high, and then this is, I'm off scale a little bit, so please forgive me on that, but 20 meters in diameter. Diameter is 20 meters. That's the diameter. Okay, it's given to be 20 meters, but for any circle, then it's more standard to indicate the radius. So 20, the meter in the diameter, that automatically means that we're looking at 10 meters in radius. Allow me not to show the math. It's elementary math stuff. Okay, and so the height here is 4, and the water start out at full. But allow me to draw at some instance. Where the water has already reached down to a level of being some y distance right here. So it's just me maybe doing math for years, and anytime it's vertical I use y, but you can break away from that as well. At this point it's not exactly about it's not particularly about the y or the x-axis. It's just about we recognize our dimension here, one of the dimension, that's all. Okay, and so the depth, the current level, okay, of water. In previous problem, in part A, I called it the current depth. Now, how about let me switch to calling that the current level. After we lift after we lift away the top slice, okay. So, and then see the top slice keep getting lifted away, okay. And then with this nice round circular shape, so that determines the shape of our top slice of water right there, okay. So now, as far as the variable, so y represents the current depth or the current level, okay, the current level of water, okay, to be lifted, the current level of water that remains to be lifted, and of course we lift the top one, so okay, and then of course it's the top slice is right at that particular level right there. And so in that way, again, just like that, now if we're looking at the side view and water is here at the level y right here, then we are going to be lifting. We lift the water at the distance, so this is 4 is the total, so we're lifting that 4 minus y. Okay, so 4 minus y to be the distance that we're lifting the top slice of water out of that swimming pool. All right, so in that way, 4 minus y, okay, to be equal the distance, okay, and of course vertical distance to lift, the vertical distance to lift the top slice, water, okay, out of the pool. All right, so that's another expression right there. So that's how far we're lifting it. Okay, so now just like that, we're gonna go find a way to calculate the volume of each thin slice of water that we're lifting out. Okay, because even though very, very thin, it's still gonna have a volume. Okay, so volume is thickness multiplied with the surface area. Okay, and so this time we know it's just a lot easier. It's actually, this problem is a lot easier than the other one. It's just also I brought this up to remind anyone doing these problems that be aware the difference between the American unit standards and then the SI unit standard in this problem right here. Okay, and so here each water slice has a surface area being a circle. Okay, being circular shape, and so now I'm looking at the surface area, okay, on the top surface, when looking down right here, then it's going to be radius 10, okay, so pi times 10 squared, that's the surface area, the area for each slice surface right there, and it's a constant amount. Doesn't matter at what level, you're at for your current level of water, you're always at pi times 10 squared or 100 pi. Easy enough, that's 100 pi. Okay, for surface area of the water. And so now with that, this is already surface area. It's not even length and width. Okay, and so now all you have to do is think about the thickness. All right, so the thickness has to be, in this case, see, we place the vertical axis here, then the thickness is going to be the change in y, because see, our variable here is y. This is y, so little change of y, right? As we lose one thin slice of water, we have a change in y. That's the thickness. So the thickness here is a dy. Okay, and so that means surface area is here. Thickness is a dy, so that means we're looking at volume, okay, of one slice. Volume of one slice is equal to 100 pi times a dy. That's volume of one slice. Okay, and then I'm going to advance over to my other board. Once we've had volume, then we're going to multiply. So we know that density was the 1,000 kilograms per cubic meter. And by the way, these are all measured in. So once we've had that volume, okay, once we've had that volume expression, this is supposed to be in cubic meter units right there. Okay, and now for our mass. So when we're going with the SI units right here, then instead of going with just straight into weight, we will get to weight eventually. But mass first, right? We have known density. So mass here is the known density, 1,000 kilograms per cubic meter. I am going to multiply with the volume previously found as an expression, 100 pi dy. Now we have our mass for one thin slice of water. So don't assume that this is big just because we have a huge coefficient here, but it all depends on how thin a dy is. So it could still be small, okay? But we're going layers and layers, slices and slices of water to be pumped out. All right, and so once we have mass of one slice right here, then we're going with the weight. So the weight, so this is weight to lift one slice, okay, of water. All right, so every step right here, we keep getting better information right here, better information. So this is now going to be, see, 1,000, or allow me to, let's not rush. So 1,000 times 100 pi times dy, that's volume, that's mass right here of one slice, but now I'm going to multiply with 9.8. This is gravitational acceleration. That there completely, that completes our force amount right here, generally expressed as an expression. Okay. So there we go. We got weights now to lift one slice of data of water, okay, out of that pump right here. Okay. So now, then that means the little work amount. It's all about we have to. So for one slice, how much work does it take, right? So work to lift. Okay. Work to lift one slice. Okay. And yes, ladies and gentlemen, I might use a slightly different wording here, but this is just the little work amount I was talking about, or this is just the dW right here. That's work to lift one slice of water. This is going to be my, 9.8. I made it a little too spaced out right there. So 9.8 times 1,000 times 100 pi, okay, times dy, but we multiply with that there must multiply with 4 minus y. All right. So, or I think it's better that I express in the bottom, in the next line down right here. Otherwise, it's going to be confusing. All right. So work to lift one slice, we call that it's dW. Again, I just now said it's small, the little work amount, infinitesimally small work amount. That's 9.8 times 1,000 times 100 pi times dy, but we need to carry that in a distance 4 minus y. All right, and so now we have our expression for the little work amount, or the amount of work to lift one slice. Yeah. So now total work is just simply the accumulation. So total work is just the accumulation of all the little work amounts, right, from the start to an end, right, of our work. And so in that way, it is going to be an integral of 9.8 times 1,000 times 100 pi times, and so allow me to swap the order of these two factors so that I want to leave the dy at the end right there. So times 4 minus y times dy. Now we have a complete integral, almost complete integral setup, and let's just now hunt for the start and the end of our accumulation. Okay, and so as we're placing our tank this way right here, and from bottom up, then so we're accumulating from y equals 0 to y equals, actually it's 4 up here because it's full of water. Okay, so from 0 to 4. All right, so start is at 0 and ending at 4 like that. Okay, so now in this one right here, at this point, we have a successful final complete integral setup like that, which is ready for action. Okay, and so again, of course, I am going to use the fundamental theorem of calculus. So in case you haven't been familiar with what the fundamental theorem of calculus is, make sure you review that. All right, so I'm gonna erase this information and use this side of the board to continue working on my integral problem. All right, so as of this point, total work W equals, and so now I have my right to write all of that as a coefficient, as a one lengthy coefficient. So 9.8 times 1,000, okay, times 100 pi. These are all constant coefficients. Now multiply with the integral from 0 to 4, and then here I'm looking at 4 minus y times dy. The integral surprisingly turns so simple once we're complete setting it up. Okay, and now I have my right to put all this away. And so now with the fundamental theorem of calculus, all we have to do now is just take the antiderivative of that. All the coefficient remains the same. The entire coefficient here. 9.8 times 1,000 times 100 pi. Okay, now I'm going to multiply with the antiderivative here being 4y minus 1/2 y squared. And we're evaluating it from 0 to 4. Okay, from 0 to 4. And so now, again, fundamental theorem of calculus says I'm going to substitute each value here in our integral limits of our integral limits into the antiderivative. So now consequently, I'm looking at 9.8 times 1,000 times 100 pi times, in parentheses, 4 times y minus 1/2 times 4 squared. Okay, and then once again, as we're substituting this this y equals 0 into the expression for the entire antiderivative, we're going to get a 0 out. So I'm going to subtract that big crazy 0 out right there. Okay, and so now in the end, it's just simply all that here multiplied with the lengthy coefficient. All right, and so I am now going to swing over to my calculation board, to my computer station and get that computed. All right, so our final answer here in exact expression came out being 784,000 pi, but all that there is in joules. Okay, so that's in exact expression. But in case anyone really want to know the decimal value of this, so pi itself, each pi is about 3.14 and longer. So all of that together in decimal value, it's 2,463,008. Okay, 0.64 joules. This is a lot of energy needed, a lot of work power needed to lift that much water out of the tank. Okay, but that's how we're done with this example. So again, just last emphasize here, but the two examples, two little problems I brought in here in this particular one example as part A and part B, they all share that similarity that instead of taking the whole water and dump it out, we can think of the amount of work done by tearing it down, bit by bit right here. And so here, each bit of water that we're lifting out is just one thin slice of water from the top. And we keep lifting it out, so we got the next one down a little less depth, lift that one out, and we got the next one down less depth, we lift that one out. So we keep lifting the top surface, top slices of water out so that we can eventually reach to the bottom, reach all the way down and completely empty out our tank right there. Okay, and it doesn't matter what shape the tank is. Some shape like this one here, get the integral set up so easy, okay, easy to recognize. But some shape like in part A, it's a little work around, but we have all that clue right there. But the fundamental is one fundamental. We break the work into little amount and then lift that out in that amount in that distance, in the distance that's changing depending on where we're at for the depth of water. Okay,